Okay, so I worry in the future we may have people who cannot come to class. So I'm also testing streaming for today. Just testing. Yeah. Uh, okay. Today we're going to introduce a different method. Now we have already learned unconstrained methods. So today is hmm, hold on. What day is today? Today is April 16th, right? I don't know why my iPad shows January 9th. I don't know why. Okay, so cool. Um, we are going to introduce one method called linear programming. It's the simplest method in constraint optimization. In the past, we didn't consider constraints, but in reality, almost all the design problem has constraints. For example, let's say we are building a chair. Uh, the size cannot be 3 meter wide, otherwise it's too large. It's for giants, and it couldn't be like 10 centimeter wide. It's too small. So size constraints for size usually is almost the constraints that you will always see in all kinds of engineering problems. And almost every parameter has an upper limit or smaller, lower limits. So that would be the most simple formulations for your constraints. And of course, you may have many different other kinds of constraints. For example, you are designing some mechanical part, but you have a budget limit. Your total budget could not be over some number. And the budget, basically money, could be a function of all the parameters that you are choosing. So you can rewrite that uh, function of your budget in terms of some mathematical equations with respect to the parameters. And that total amount must be smaller than some value. So from here, you can already tell in reality, there are always constraints. So if you try to use Newton's method or steepest descent or conjugate gradient to solve these problems, you cannot handle the constraint. So that would be a big problem. So now let's review how a optimization problem should be written when we have constraints. So usually we handle minimization problem. So objective function f, and we wrote st right here, which means subject to. Subject to means you are limited by certain things. And you start to write down the constraint functions. And over here, we usually like to use g functions. And we try to formulate g functions in certain way. So usually it looks like some g function smaller than a number of zero. Or, and also, we have h functions. They are the equality constraints. So we don't have larger than or smaller than, we have equal sign. And we categorize G and H separately. G are constraints that has a larger than or smaller than. The H functions are equal sign. Okay, so they are so-called the inequality constraints, and H are the equality constraint. Okay, that's the most usual formulation that we have. So let's right now start to think about some very simple problem. Uh, let's say we are trying to design maybe a box. So let's say we have a box, okay, and the width of the size of the box could be defined by x1, x2, and x3. So the total volume of this box could be x1, x2, and x3. Okay, and maybe for some reason we wish this box could be placed in a container, and probably it's a circular container. So just some story I made up. We wish this box could be placed in a spherical container. So the only way this could fit in is that the widest range of this box should be smaller than the diameter of the sphere, right? So what is the widest range? Basically the diagonal, right? So let's say I have a diagonal uh, range. That range equals to square root of x1 square plus x2 square plus x3 square, right? And we wish this should be smaller than some number. So let's say there is some value d. We wish that uh, my design has to be within this range. Okay. So what could we do next? So probably you're trying to find the largest box that fits in this spherical container. So in this case, actually you try to maximize your volume, but you have this constraint. And maybe you need to also set up some limits for x1, x2, and x3 so that you won't have some design that looks completely strange. So maybe all the x1, x2, and x3, they must be, for example, larger than or equals to some number 2, just some random number, and maybe smaller than, I don't know, maybe the maximum possible value. So basically D. Okay, so let's say I have those designs, and for some reason, maybe you wish um, two of those sizes is in certain ratio. Maybe you are trying to use this box to keep some of the objects that is always having certain aspect ratio. So maybe x1 always equals to 3 times x2. It's possible. So let's say you list out all the possible functions that is related to this design, and most importantly, you have a goal. You have a design objective. So in this description, basically, this is your objective. You try to find the largest, I mean the box that has the largest volume. Okay, and also those are the constraints. Okay, and if I try to reformulate this whole thing into the standard format, how would this whole thing be written? And like we usually do, we like to handle minimization problems. So in fact, when we describe this problem into the standard way, we need to convert this maximization into a minimization problem. So your formulation could be, so you actually formulate a f function that equals to negative value of the volume. Because minimizing the negative value of some function, that basically is equivalent to maximization of that function. Okay, so uh, in optimization, you are the designer. You have the power to design your problem. Actually, in fact, you have the responsibility to formulate the problem. Problem formulation usually is more important than solving it. Because when you derive it, when you formulate a problem, the solution I mean, I should say, probably there is only one solution. And you can use many different ways to find it. And all those methods are just mathematical tools like what we introduced in the class. And if you formulate a problem that has no solution, then no matter how good your method is, there's no solution. But if you have a problem that has so many solutions, 1,000 solutions, your method probably can only give you one. So what do? You have your solution has no intelligence. Your method has no intelligence. Either the method could tell you there are 1,000 of them, or the method give you one or some of them. But the method doesn't give you suggestions of which one is the right one. You designer, the designer, should take responsibility. Okay, so once I have this, how about the constraints? So we could do this. We can say I have a G1 function, which is equals to minus D smaller than 0. Because we like the formulation of smaller than or equals to 0. So we can rewrite this D, move it to the left, and then rewrite in this way. So can we rewrite this in a different way? Actually, yes. We could also rewrite in a different format like this. Which one do you like? The bottom one. Someone said the bottom one. Why do you like the bottom one? There is no square root. Okay, but how come you don't like square root? Because when you have, okay, what kind of function is this? Polynomial. Polynomial. This is a nonlinear problem. This function is more nonlinear than a polynomial. So when the shape of the function is more complex in the mathematical way, usually it's harder for the method to handle it. Like I think in our second or third problem, we handle the log, and you can tell if we choose the wrong starting point, sometimes the solution process explode, and then you cannot get solution. So if we always handle nicely formulated, well-developed polynomials, it's nicer. And you, as the engineering designer, should take the responsibility to decide whether I use this or that. So our responsibility is very important. And for uh, technicians or mathematicians who did not take courses in optimization for mechanical engineering, usually they only learn how the solver is derived and how the solver is used to solve the problem. Usually they don't focus on how the problem should be formulated. But actually in engineering, this is actually more important. Like myself, I publish papers about uh, different kinds of design optimization problems. And actually, my main contribution probably is how I formulate the problem. I don't actually focus on which solver should be used to get the right solution. Because for us, when we have the right formulation, the solution is there. We just need to spend some effort and then get it. Okay. Now, how about my G2? From here, you can see uh, every G function right here only has one inequality sign. But when we talk about this one, there are two inequality signs. So to be precise, we actually need to describe the left-hand side and the right-hand side, both of them, separately. So our G2 could actually be 2 minus x1 smaller than 0. So that basically is this part. Okay? And our G3 could be 2 minus x2 smaller than 0. And so on. We have actually totally 6 of them. Let me try to describe one of the constraints on the right-hand side. So let's say my G4 could be x3 minus d smaller than 0. Okay, so that's basically this one. So there are many of those. And we try to formulate what we think about in the standard way. And no matter how many there are, we just keep on writing them down. Okay? And how about the last one? This is a equality constraint. So for us, we write in this way. So we put them together and then claim this function as equals to 0. Okay? So this is how we should reformulate a true problem into mathematical format. And when we have those, a bunch of mathematical equations, and we introduce methods to handle those. And today, we're going to use linear programming. Is this clear enough? Okay, let me move on. And I need my notes. So linear programming. Okay. Okay. So for linear programming, it's difficult for linear programming to handle inequality constraint. Linear programming can only handle equality constraint. So what should we do? So we need to kind of make this problem be rewritten in a different way so that we can treat all kinds of problems in this standard format of equality constraints. And let me show you how. Okay, so let me see where it is. So first thing that we need to worry about is LP, linear programming, doesn't handle inequality constraints directly. So that's a problem. We need to transform those functions into equality constraints. So need to reformulate them to equality constraints. So that's a very important step because from previous problem, we can see a lot of inequality constraints. How could we transform them into equality? Over here, we're going to introduce something. Let me find the exact note for that. Not in this one, maybe this one. Ah, here. So we're going to introduce something called slack variable. Okay. So what is a slack variable? Let me give you one example. Let's say we have a function like this. Something like that. And when we introduce a slack variable, we actually create a artificial variable into the problem, and then we put this slack variable into this function in this unique way. And what we do will actually give you a totally different formulation, but completely equivalent to the original problem. So how do we do that? So when we introduce this, we rewrite in this way. We keep the same thing, but on the left-hand side of the equation, we add one more variable. Let's say slack variable 1. And on the right-hand side, we change the whole thing into equal sign, but keeping the value or keeping whatever on the right-hand side there. So we basically only just add one more variable on the left-hand side and enforce this function becoming a equality constraint. But when we do that, we actually need to make sure S1 has to be larger than or equals to 0. Okay? So think about this. When we have S1 equals to 0, that means the left-hand side equals to 3. When we have S1 larger than 0, that means the original left-hand side plus this, some value larger than 0, equals to 3. So whatever is over here must be smaller than 3, right? So in this case, either this thing is equals to 3 or it's smaller than 3. So the combination of these two new equations basically are equivalent to the original one. But when we do this magic, we convert the formulation from inequality to equality. And that's how mechanical engineers who knows optimization can be very different from other people, because we know how to do this. Okay, that's this course. The importance of this course is that you learn some tricks to reformulate your problem. Okay, that's the first trick. And the other trick is something called the surplus variable. And for the surplus variable, basically, it behave in a different way. So usually it's utilized in the other kind of problem where you have larger than in this case. So what we do is we keep the whole thing, and then, oh, this is 2. This time we minus T1 and make it equals to 2. Here I should have equal sign. And we need to make sure T1 is still larger than or equals to 0. So in linear programming, it's important that all the variables are larger than or equals to 0. That's why we try to put the negative sign here, so that this whole thing is equivalent to the previous one. By the same reason, if you test it, if T1 equals to 0, this left-hand side equals to 3. If it's something larger than 1, then whatever is over here must be larger than 3. So in the end, whatever is over here is either equals to 3 or larger than 3. So that's very simple, okay? So in your exam, in the future, when I give you an exam, you need to know how to convert inequality into equality. If you made a mistake right here, you basically get 0 point. Because this is like a first step, very first step. In your exam, this is a problem you will be solving, okay? And probably the only problem you will be solving. So very important. Don't make a mistake at this point. Okay, so when we are able to convert all our variables into, all our constraints into the equality formulation, then we can review our problem again. But there's one thing that we haven't introduced yet, which is the linearization part. So the key of LP depends on linearization. We basically linearize everything. Okay? If you look at what we had earlier, is this a linear function? Anyone? Linear or nonlinear? This is nonlinear. When you have two things multiplied together or more things multiplied together, it's nonlinear. Linears are like x plus y plus z, only plus or minus, no multiply. Okay? So this is nonlinear. This, of course, nonlinear. you can tell this is a second order problem. What does linear function look like? When you make a drawing, it's a line. That's why it's called linear. This is linear. Okay, so this one is okay, but this one is no good. This one cannot be directly handled by LP. The objective function cannot be handled by LP. So what do we do? How do we linearize a nonlinear problem? What's what what's the trick that we usually do? Say again. I didn't hear you. No? Some famous person's expansion? Taylor expansion. Yeah. So I think in optimization, the most important calculus you need to know is Taylor expansion. And and of course, partial derivative. And pretty much the rest are based on those. You don't need to solve very difficult differential equations or like time dependent no something like that. It's only based on very fundamental calculus. So how to linearize a function? Just based on first order Taylor expansion. Okay, and no matter it's a 1D problem or multi-dimensional, you can always use first order Taylor expansion. So any function, this is a vector form, so it works for any dimension. Basically, can be rewritten as this. This is how you could get a linear function, no matter what the dimension is. X0 is your expansion point. Okay? Sorry. So shall we give it a try? So let's say I have this function uh, f equals to x1, x2, and x3. And let's say I want to make a very simple linearization of this function at certain expansion point. So let's choose some expansion point at, let's say, 222, okay, some random number. So what would be the linearization of this? So I use Taylor, first order. So over here, you should have your f of x0. So basically, your expansion point and plug in. So when you do the plug in, you have this. Okay, plus a vector minus your expansion point 2, dot product the gradient. So what would be the gradient look like? So the partial derivative with respect to x1 gives you x2 and x3, and the second one gives you x1 and x3. The last one gives you x2 and x3. And over here, you need to plug in x0. You need to plug in your uh, your expansion point, right? So what does this whole thing look like at the end? You have 8 plus x1 minus 2, x2 minus 2, x3 minus 2. Dot product, when you plug in, you basically have 4, right? And expand this whole thing, you have 8 plus 4x1 minus 8, yes, plus 4x2 minus 8 plus 4x3 minus 8. So at the end, you have 4x1 plus 4x2 plus 4x3 minus 16. So that's how you convert the completely nonlinear function into a completely linear function based on the expansion point you chose. So very important, you practice this. Previous step is to convert your inequality into equality. Another thing that you need to do is linearization. Because in my problem, I won't give you some linear problem directly. I will ask you to do Taylor expansion. Okay? So, once you have those two, you then can rewrite your original problem into the next formulation. So your LP standard format looks like this. Okay. Oh, this is should be, and also uh, x1 to xn must be larger than 0. And also we wish b1 to bn also larger than 0. And usually you have m smaller than n. So we have totally n equality constraints, sorry. N equality constraints, and we have n variables, right? And also we wish all the variables must be larger than 0, and we need to reformulate this into a certain way so that on the right-hand side of the linear functions, we want to keep those constants to be positive. And usually, the number of equations will be smaller than the number of variables. So what will happen if m equal to n? Does anyone know? If we have same number of equation and variables, what happens? You will have your solution, one solution, right? Remember when we try to solve linear equations, when we have the same number of unknowns and same number of equations, we have one solution, right? Or maybe we have no solutions when they are parallel or the same line. But if there are different lines and they basically overlap at one point, so that's the only point that satisfies all the equations. So if we have same amount, basically you don't need to do optimization. You can directly solve and get a solution. And What if m is larger than n? So you have more rules than the number of unknowns. So basically, no solution. Too many rules. So we usually call this, if it's larger, it's over constraint. And when it's smaller, we usually say it's under constraint. So in other case, when m equals to 0, sometimes we say fully constrained or completely constrained. So usually you have one solution, one possible solution. So when this is larger, it's over constrained. So if it's over constraints, there's no solution. In most of the cases, there's no solution. So when it's under constraint, what does that mean? That means there are infinite possibilities. So when there is infinite possibilities, then we could have the opportunity to find the best one. That's why optimization can play a role. Okay, so let's take a break, and when we come back, we start to talk about LP. Okay, take a break.